have daytime activities that go on where people do solar viewing, or they have different particular information, lessons in astronomy, or different other kinds of information that they share. Some are specifically directed to children, and some are directed to all ages. And so, okay, so good. So it looks like we are ready to start. Is that right, with our speaker? Okay, wonderful. So now, tonight we have our guest speaker who is going to talk with us about some really special things and his history that he's been working on for a long time. His name is Bob King, and he has been a longtime member of the American Association of Variable Star Observers. And he is coming to us tonight from Duluth, Minnesota. So, our Zoom connection seems to be doing fine between the two areas. So I think we're ready to start with Bob.
Thank you very much for that very nice introduction, and it's wonderful to be here. It's an honor for me to be able to speak to your group. I really enjoyed Tucson. I've been down to the mineral show, and because I have a particular fascination with meteorites, so I've been down there and checked all that out, and I've camped down there as well. And it's the first place I finally got to see the star cluster Omega Centauri was from the Tucson area. So great to be with you tonight. I'm primarily a very hardcore deep sky observer. I have a 15-inch obsession telescope and a bunch of other scopes, too many to count, kind of like some of you. However, I find the naked eye aspect of observing just as interesting as the deep sky part, or even the astrophotography part. And so I'm just going to talk tonight about several little, I call them projects. I sort of assign myself little projects, kind of like you do as observers. You might say, well, gee, I want to look at a certain type of galaxy, or maybe I want to do some lunar observing tonight and look for all the different domes that you might see on the moon. So I'm going to talk about 3 little observing projects that I found entertaining and that have given me a lot of joy. You know, it's anytime we make a connection with nature, you know, and that means some involvement with nature, whether it's deep sky at the telescope late at night, or if you're just out looking at some of the things I'm going to talk about, that connection is what gives us a lot of joy. So with that, I will start with the presentation. And it's called Eyes Only, Fun Observing Projects with Minimal Equipment. The things that we were born with, our eyes. All of us started out that way, looking at the night sky. By the way, am I sharing my screen? Hold on. I want to make sure I'm doing that.
Not yet, Bob.
Not yet. We'll do that now. I'm so excited. I forgot to share the screen. So now you should be able to see my screen. I apologize for that slip up. And we all started with observing the night sky with just our naked eye. That's what got us involved for so many of us, is just looking up and enjoying the sight of the sky, of the stars, and wanting to know what that star was, what that pattern was. And then we kind of fell into it from there and got deeper and deeper and learned more and more. One of the things that I think we've all seen, and I imagine most of you are familiar with, is the Earth's shadow, which rises in the eastern sky directly opposite the sun when the sun sets. And you can see it here on a road near my house. It's just so ubiquitous. When I point it out to non-astronomers, they're sort of amazed, like, really? That's the shadow of the planet cast on the atmosphere? And indeed, it is. And you can see it here, kind of a steely blue-gray along the bottom. And then it's topped by this orange coloration called the Belt of Venus. And what that is scattered light from the setting sun being reflected, or not reflected, but scattered from the atmosphere towards our eyes. I have seen the Earth's shadow and that beautiful glowing pink orange band from many places on the Earth, not just my local roads here at Duluth, but also I had the opportunity to see a very lengthy Earth shadow duration when I was down in Antarctica back in November of 2021. And the sun only dipped briefly below the horizon. And so the Earth's shadow and that beautiful color that was visible all night long, although the night was short, but it was gorgeous with the glaciers. What causes the shadow, what makes us able to see it, is just basically the bulk of the planet. And the bulk of the planet is blocking the sun as it dips below our local horizon. And on the opposite side of the sky, the Earth's shadow rises, and we see it projected against the atmosphere. And as topping it right here is that beautiful pinkish orange belt of Venus. And of course, it has nothing to do with Venus, and I won't go into the possible origin for the belt of Venus, but it is caused by sunlight that from the height of the atmosphere, even though we're in shadow, from the height of the atmosphere, it is scattering back that orange-red glow of the sun. And so we see that edge to the shadow. I've seen the Earth shadow many, many times, probably many of you have. And on flights, I've noticed that it is far more distinct. In fact, it's very, very dark. It almost looks like a thunderstorm approaching. And in this photograph, taken by Wes Colley, really captures that well. We see the full moon right here, and look at the darkness of the shadow. And the reason why it's particularly dark from an airplane, and it's something to watch for if you're ever on a flight, is because there's far less dust. We're looking through a much more transparent atmosphere. And so the contrast the shadow makes with the sky is far more dramatic. Also, I think, although I'm not 100% on this, it's possible that at a higher altitude, we also have a longer line of sight into the shadow, which could increase the degree of darkness that we see compared to a view on the ground. But it is something really to watch for. And so this was the first extra thing I noticed about the Earth's shadow. The other thing that really got me interested in starting to explore it more deeply was I would see what I thought was the shadow before the sun set. And I kept noticing this and thinking, well, it's not possible to see the Earth's shadow before sunset, is it? You have to have the sun below the horizon to cast that shadow onto the atmosphere. But then I learned that the atmosphere itself, with all of its particulates and aerosols, actually acts like a screen. And we look through it and it absorbs light, especially near the horizon, where we're looking at the bottom of the atmosphere, the densest part. And it creates sort of a false shadow. Here you can see it in this picture. I took this right here on Lake Superior, where I live. I live a few miles from the lake in Duluth, Minnesota, 6 minutes before the sunset. And we've got this atmospheric shading, and we also have the start of the belt of Venus. Again, that scattered light from the setting sun. Here's the shadow proper, 1 minute after sunset. Very different. You can see the change there back and forth. You notice it's much denser, darker, and steely gray blue compared to that sort of hazy gray that's actually cast by the atmosphere upon itself. I decided it was time at this point to explore the shadow in a little more detail. And so a year ago, I went with some friends to the panhandle of Oklahoma, which is, I believe, we weren't very far from where the Texas Star Party was held. We were at a place called Black Mesa back on February 28th. And the guys told me, said, hey, Bob, you're going to have a perfect horizon. Well, it wasn't perfect, but it was pretty close. So I had a nice view to the east, opposite the setting sun, and took this picture right at sunset, where you can begin to maybe just see the edge of the Earth's shadow and the belt of Venus appearing. And then I took pictures every 3 minutes. Here's 3 minutes after sunset, no question about it. There's the shadow, there's the belt of Venus, and kept going along. And right around here at 6 minutes, the shadow was really dark, very prominent, the belt of Venus, very colorful. And then you notice kind of something peculiar happening at 9 minutes after sunset. Not that this happened every time I've seen the shadow, but there was this sort of asymmetry in the shadow shape. Okay, where the sun's right at my back, and instead of being a symmetrical dip along the horizon, and by the way, the shadow does extend 180 degrees across the sky, one side was a little higher than the other. And I'm still not clear as to exactly how that happened. I hypothesized maybe there were some clouds way below the horizon that potentially casted shadows that mingled with the Earth's shadow. But at least at our location, the sky was perfectly clear. You're now at 9 minutes after sunset. The belt of Venus is fading because, of course, the sun is dipping lower and the shadow is rising higher. So we are now looking through less and less atmosphere, and the sky is darkening. So the contrast is beginning to drop. It's very noticeable 12 minutes after sunset, this change in the contrast and the fading of the belt of Venus, because there's less sunlight. The sun is below the horizon, even from the atmospheric altitude, and we're looking through less atmosphere. So there is less backscattering of whatever sunlight there is left. But this is something that was remarkable to me that I had never noticed before. Beneath the dark shadow, I expected it to just be darker yet, but instead it appeared lighter. You could just start to see it here 12 minutes after sunset. 15 minutes after sunset, I hope you can see the difference in my slide. It's a kind of a pale zone down here, and the shadow becomes more of a belt slung across the sky. And I don't know the exact reason for this. It really got me looking online to see if I could find a source for this. And I did find a couple of additional photographs showing this phenomenon, but I was not able to get an explanation, which excited me greatly because I thought, well, what could cause it? You know, we all like a little temporary mystery as amateur astronomers. And so all I could figure is that we're looking again through the very bottom of the atmosphere. So we're seeing additional scattered light. That light is sort of softening and diluting the darkness of the Earth's shadow. That's particulate matter, that's the atmosphere itself. It's beginning to absorb that light. Again, I don't know if this is correct, but it's just my own surmise. And maybe one of you might have the answer to this, which would be great. Feel free to chime in at the end. Here's 18 minutes after sunset. The belt is gone. You can still see the shadow, but the contrast is quite low now. However, the pale part of the shadow, that lighter area, is now very easy to see. Again, it was a complete surprise. And I think part of my pleasure in seeing this was I'd never noticed it before, and it was just something that was visible with the naked eye and maybe worth a little more research down the line. Now the top of the shadow merges into the darkening sky 21 minutes after sunset. And really, by now, it's extremely difficult to see the shadow. It's pretty much gone, invisible to the eye. But there is one circumstance I'm going to show you where the shadow actually can be seen moving all the way over above your head and into the western sky. I'll show you that in just a second. So here is an animation. I just put a bunch of the slides together so that you can watch the process yourself and enjoy watching the cows move around in the foreground in the field there. But you can see how the shadow is changing. We'll do one more. I'll tell you when it starts there. And the symmetry. There's the lighter layer. And there it begins again. So this is a higher contrast version of that curious observation where there's a darker band and a lighter shadow beneath. And again, my question is, what is the cause of the lighter band? Pardon me here, and exactly what causes that asymmetry in shadow height? This is something that I plan to go into more, and you might be interested in this yourself and delve into it and make it something to produce new knowledge from, potentially. So I told you about a very special circumstance with the shadow, and normally disappears from view into the sky as it darkens. But every once in a while, when we have a powerful volcanic eruption, that spews volcanic aerosols, various sulfur compounds, way high into the stratosphere. I mean, we're talking like 20 plus miles above our head. That material is high enough so that it will reveal the presence of the Earth's shadow, even as it moves over towards the western sky, as you can see in this sequence of photographs taken by Doug Zubinel. Here's on slide 1. 2, the shadow's moving in. 3, it's about covered the whole sky. And 4, and this would ordinarily not be visible, but when we have massive eruption, even though it can add a lot of stuff to the sky, which makes it difficult to see stars, fainter stars, it does reveal the presence of the Earth's shadow all the way across the sky, which is just an amazing observation. So this is just one of the 3 little projects that I've been involved in. The second one is about measuring naked eye sunspots. And this is going, when I'm done with this, you're going to say, well, of course, that's easy enough to do, no problem. But I'd always seen comparisons, like it's 5 Earths wide or as big as Jupiter or whatever. And I thought, well, how can I measure sunspots? Because I love observing the sun. It's one of my favorite things. I have just a really small University Optics 3-inch refractor from way back when. And I've got a glass filter on it. And I use that to observe the sun every clear day. It's on a tripod. I set it out and I look and see what's up. If I see big sunspot, I get my camera out, push that thing right in the back and take a picture. I also have a Lunt 40 millimeter H alpha scope that I'll use too. When the weather warms up here in Duluth finally. But I like showing the sun to the public, at various star party events during the daytime. And so I always like to know how big that sunspot is. So I can just tell somebody there, well, that's 3 times the size of the Earth. So just a little bit about sunspots before I show you my methods. I look back to see the early records on sunspot observation, and the earliest ones that we have go back to the Chinese observers. This particular painted panel here is from around 1100 AD, and the sunspots back then were described as, the frequent descriptions were to describe them and compare them to plums and goose eggs, which, I mean, maybe goose eggs and plums were a lot smaller back then, or else sunspots were a lot bigger. But those were terms, or are terms, that you'll see in the description of naked eye sunspots made by early Chinese observers. The first written record of a sunspot goes way back to 28 BC. We also have the first telescopic observations of the sun and sunspots were made by Thomas Harriot in England, and Galileo somewhat later, in about 1612 or thereabouts. Here we have a number of Galileo sketches of sunspots, and I put them together to make an animation. He sketched the sun very regularly. He was an ardent observer of the sun. And you can see some of these are so big that clearly they would have been naked eye sunspots if you or I had held up a filter nowadays to take a look. His observations here were made between June and early July of 1613. And you may have read that Galileo went blind because, he looked at the sun without a filter. However, that is not correct. As it turns out, the actual reasons are far more mundane and relatable. Galileo lost his sight through kind of a combination of cataracts and glaucoma. And in fact, the way he observed the sun was either right near sunset or sunrise, when its light was attenuated, being near the horizon, or he used the projection method. That was very common for him to use. So he did look at the sun quite safely, as it turns out. The largest sunspot group visible in modern times goes back to April 1947. And here you have this massive group. Can you imagine how big this would look just with your naked eye? I mean, I was born 6 years too late. I didn't get to see this. Here we have Jupiter for comparison. There's the Earth. Obviously, this entire sunspot group, this whole region here, is indeed larger than the girth of Jupiter. We are currently in a wonderful part of the solar cycle It's advancing, rising beyond our expectation, the initial prediction for the cycle. You can see this is the initial prediction, the red curve for solar cycle 25, the current cycle. And this is where we were back in December of 2022. We were well above the official prediction. So, and any solar observer knows that in the past year, there have been lots of naked eye sunspots, very large sunspot groups, and tons of solar activity, I'm even more excited about the current year, 2023, and what it will bring. This is just a series of photographs I took of naked eye sunspot groups. They're in the red circles, of course. Each one of these regions or single spots was visible with the naked eye using a safe solar filter. And you'll see in a moment, my filter of choice is just what you could pick up at the welding supply shop, a number 14 welder's glass. Just look at it, it's like every month. So this past year, and it's continued on into 2023, we've had an additional several very nice naked eye sunspot groups. At the moment, the sun has got some groups visible, but nothing really pronounced at the moment. And this is what got it all started, this triple 3 large spots. We've got 2 regions here, 2994 and 2993. This photograph, I took it through my refractor back in April, 21st of April in 2022. And here is a shot of the group rotating onto the disk. And it was, once it got away from the limb of the sun, where it was highly foreshortened, these 2 regions were visible like every single day of the week that it was clear. I could look up and see these groups. There it is. There's the device of choice, the number 14 welders there with my daughter. She's doing some solar observing with me. Here's the view. I tried to make a sketch to show you what it looks like through the welder's glass. Those groups were large enough that I could see for sure 2 dark spots, kind of like an inverse double star, 2 dark dots next to each other. And I just suspected that 3rd spot, but I couldn't be certain, so I did not include it in my drawing. The welder's glass, by the way, makes the sun's image green. If you don't have a welder's glass or there's no supply store near you, I know Rainbow Optics sells a number 14 built into a very large card, which is super helpful because you can just hold that card right up against your face and it blocks all of the ambient light. Blocking that ambient light is really crucial to making naked eye sunspot observations, which is what we're talking about here, is how to see and measure naked eye sunspots. Now, if you want to, let's say you use a number 14 or a telescope or whatever you use, and you see a particularly large sunspot and you want to know how big that thing is. Well, you could take a picture of it like I do and do your measurements, or you can let NASA's Solar Dynamics Observatory take the photos, because it's taking multiple pictures of the sun in various wavelengths of light every single day of the year. You can go to this website and select this image, which is a very flat image with a sharp edge. It's called the HMI intensitygram, flattened. Just go down the list and pick this lovely yellow disk of the sun. Here it is, blown up on your screen. And when you open it in Photoshop, I use a very basic Photoshop Elements program. And these next few slides are going to show you how to basically put a ruler in your Photoshop window and measure the width of the sun and any sunspot group you like in pixels, basically a pixel ruler. There's a much simpler method for doing this. So if you're totally uninterested in using Photoshop or imaging like this, no problem. I got a quick way for you too. But to measure the sun, you can go into Photoshop or a similar imaging program and open up your preferences. Under preferences, you just pick units and rulers, and there you select pixels. My Photoshop defaults to inches. I do everything in inches. So I go in here deliberately to pick pixels because a pixel is a much smaller unit And I like much smaller units for measuring things like sunspot groups, as you'll see in a moment. So you pick pixels, and then you go under the view heading and select rulers. And when you do that, you come up with your sun, and around the sun is a ruler in pixels right there. You know where I'm going with this. This is very handy. Here's the tool that you're going to be using. This is basically the brush tool in Photoshop. Is basically like, we're going to use it like a tape measure, all right, and measure the pixel width of the sun and then the pixel width of a sunspot group. First, you have to take your cursor and move it into the corner at the 0 point, hold your mouse button down, and then drag that corner over to the edge of the sun so that the 0 point is right here at the limb. That's the 0 point. And then it becomes a very easy matter to measure the width of the sun, its diameter in pixels, which in this case is 950 pixels, right? Very simple. Then you zoom in, plus, whatever magnifying glass, enlarge the sun, reset your 0 point using your mouse cursor, holding down, dragging it over here, let go, and then bingo, it becomes 0. Then you measure the width of the sunspot group, 38 pixels in this case, okay? Then it's super simple math. We know that the Earth is 1/109th the diameter of the sun. So one Earth diameter is equal to 950 pixels divided by 109, or 8.7 pixels. So that means that sunspot diameter is 38. You recall that was what we measured, divided by 8.7 equal 4.3 Earths, or about 34,000 miles, which is really cool. You can look at it and go, wow, that thing is 4.3 Earths in diameter. That is huge. So it's such a simple operation. And it's even easier. You can just take and print out a picture from the SDO site, the Solar Dynamics Observatory site, and then just get your millimeter ruler out and measure the equator, or not the equator, I should say, but measure the diameter of the sun, and then very carefully measure the width of the sunspot group. And in this case, we have 120 millimeters, right, divided by 109, because they're this 1/109th the size of the sun, you get 1.1 millimeter. 4.7 divided by 1.1 equals 4.3 Earths, or approximately 34,000 miles wide. Now, this is ballpark only. We're not talking exact numbers, obviously, just to kind of give you a sense of how big that sunspot group is. So, of course, over time, I've been curious, how small of a sunspot group can I see with my naked eye? And what is so funny about this and doing it is that you hold the glass up and you look and you block out all of the other light. And before long, you find yourself doing things like using averted vision. Honestly, you use similar techniques to see a very small naked eye sunspot as you would trying to see a faint star. I know it sounds counterintuitive, but it works. And in doing this very simple method, I've discovered that the smallest naked eye sunspot I've been able to see so far, just sort of right there at the edge of vision for me, is about 21,400 miles across. And this just happened recently on March 24th. We had a really spectacular array of sunspots in late March. Look at these three together, big triangle. Over here, I have the sun's apparent size in SDO images at perihelion, at the two equinoxes, and also at aphelion. So if you wanted to just photograph this slide so you have those numbers, then you don't have to measure the sun. You can just get that ballpark image just by measuring the width in pixels of the sunspot group and doing the simple division problem. And you can actually see this on images. I checked them all out. You can see that the sun is bigger at perihelion in the SDO images and smaller at aphelion. There is the problem of foreshortening. When a naked eye, potentially naked eye sunspot group is near the solar limb, it's extremely difficult to see, even though it is a large group, let's say. but it needs to rotate closer to the center, more face on, not only to become apparent to the naked eye, but also to get a semi-accurate diameter or size. And so I have the sun here and I put in the useful zone, as you can see. And since many sunspot groups fall within this zone, it's not uncommon to see a sunspot group pass through this useful zone so that you can get a reasonably accurate measurement of its size. Here's something fun you can do too. Actually, I have to say, I'm not doing this, but I have enough data to actually start a curve. But this is, you can make your own plot of the 11-year sunspot cycle without a telescope by just using that glass, or you might use eclipse glasses, whatever works for you, naked eye, and noting each day you see a naked eye sunspot and counting that, and then graphing it. And as this group did in Belgium, and they came up with a curve showing the number of the naked eye sunspot groups parallels the yearly mean sunspot number. So it's just sort of fun. A tiny shred of science in this is possible as well, plus your own edification and the ability to share that information with the public is a lot of fun. And my final of the three different visual projects involves the Milky Way. And this is from just north of town here on a lake out on their dock, and oh my gosh, the Milky Way was just spectacular that evening. So I quick got a tripod and took a picture. This is, our galaxy is a spiral galaxy, perhaps not as delicious as this. Every time I see this, I wish I had one in the refrigerator ready to go. A more accurate model of our galaxy shows it to be a barred spiral with a dense bar of stars for its nucleus or core, multiple spiral arms. It's an enormous object, as we know, roughly 105,000 light years across and approximately 10,000 light years thick. So it's very large and it's very thin. In a sense, it resembles our own solar system, and it formed in a similar way through gradual condensation and compression and spreading, because of the angular momentum spreading out into a flattened disk. Here's a photograph that you can see showing the full width of the Milky Way, all right, from northern hemisphere through the central bulge in the constellation, toward the constellation Sagittarius, and then out into the southern hemisphere. So you get a sense just looking at this mosaic that our galaxy is quite flat indeed, and that it does have kind of a bulge in the center. Of course, many stars are missing from this image because of all of the foreground dark nebulae. Here you see them strung across, absorbing so much starlight in the background. Here is the face-on view of the Milky Way. The sun is located approximately 26,000 light years from the center, or roughly halfway between the center and the edge. Here's an edge-on view. When we look at the winter Milky Way, we are looking out through the galaxy towards its edge, which is one of the reasons the winter Milky Way looks a lot fainter, like the part that goes from Cassiopeia through Auriga, Gemini, Taurus, Orion, so forth. When we look towards the center of the galaxy, we are looking to where the stars really stack up, to where there's a greater density of stars. And the summer Milky Way is much more prominent than it is compared to the winter sky Milky Way. And naturally, what actually defines the band of the Milky Way when we look at it in the night sky is when you shift your gaze to look above it or below it, you're looking into intergalactic space. And so you're looking away from the galaxy. And that's why there are far fewer stars and no band is visible there. The band is only visible because of the relative thinness of the Milky Way and the fact that we're looking right through the very equator of it all across. This is the diagram, which I know a lot of you have probably seen, and which was an inspiration for me and really helped me to find my place in the Milky Way galaxy, because that's what this is really about, is where am I in 3 dimensions in the galaxy? Maybe you've looked up too and thought it's just all overlaid. All the stars are in front of other stars. You can't really pick out the spiral arms because we're seeing the whole thing virtually edge on. So you can't see the structure. So I've always kind of wanted to know, where am I in the galaxy? Can I get a better idea of the structure around me, other than just knowing that the center is towards Sagittarius and the edge is towards Taurus and Auriga? So I use this longitude map, and just like a longitude map on the Earth, okay, we've got numbers around the circle. 0 degrees is the longitude of the center of the galaxy in Sagittarius. 90 degrees longitude, you're looking off towards the constellation Cygnus, the Swan. 180 degrees, Taurus, Auriga, you're looking to the edge, or what's called the anti-center of the galaxy. One of the coolest words in the world, by the way, anti-center. Here's a part of the galaxy we don't generally see because we live too far north. It's covered by the curvature of the Earth, the constellation Vela and Crux and Centaurus. This section of the galaxy is off towards 270, and so on. This map is available right here at this link, and very easy to look up too in Google search. So if we look at a constellation map to locate the center of the galaxy, we're looking off the end of the teapot of Sagittarius. That's the direction of the galactic center. That is galactic longitude 0. And galactic longitude 180, the anticenter, is right at the border of Auriga and Taurus, not too far from the star El Nath. For a little more detail, and anytime you want to know what particular longitude you're looking at and what constellation or part of the sky that is associated with, you can go to a stargazing app or program. I use Stellarium a lot, and go into the markings section where you can add in an azimuth grid or the ecliptic or whatever you like, and go to the galactic equator and fill in all those boxes with check marks. And when you do, it will show you, well, the Milky Way is always there. It's part of the program view, but it will show you the galactic equator, you know, the line that goes right through the plane of the galaxy. And then along with that, you can read off the various longitudes. Let's put all of that information into this one picture. This is one of my favorite views of the Milky Way galaxy, obviously just a model, but it's very effective in terms of getting a sense of where you are in the galaxy when you're out under a star-studded sky and you're looking up at that magnificent band of starlight above your head. Here we are in the sun. Again, when we're looking towards Sagittarius, we're facing towards the center. We look down a spiral arm when we're headed, when our gaze faces off to the summer triangle, which is now just coming up in the morning sky. So the Milky Way is starting to make its way back into the morning sky. I saw it the other morning, as a matter of fact. When we turn around and face more towards the north, we're looking into the Perseus arm of the galaxy towards Cassiopeia. We're beginning to look outward from that position at 120 longitude. And if we make the full turn away from the center, we're looking outside to the edge of the Milky Way. And we keep turning, and pretty soon we're facing towards Canis Major, back into the Perseus arm, and then towards Carina, if you can see that part of the sky where you live, into the Sagittarius arm, and then back around in a circle. So combining those longitudes with the knowledge of where we're at in the galaxy helps us to get a sense, as we sweep across the band of the Milky Way, of how we're located in space. And with a little imagination, we can picture the spiral arm sort of buried within that starry belt, that band. And of course, it does take some imagination, right? Because we can't see this stuff directly, because we can't get above the plane of the Milky Way. Speaking of planes, there's one other interesting fact that will help us understand how to perceive where we live in the Milky Way galaxy. And that is to understand the plane of our solar system. A very easy concept. All the planets orbit the sun fairly close to the ecliptic plane, which is basically defined as the Earth's orbit around the sun. So this is just a model showing that. Interestingly, and it's almost like a holdover from the days of the pre-Copernican days, we intuitively, at least I've noticed this when I teach it, intuitively people think that the solar system is sitting in the galaxy aligned with galactic equator. You know, we're all on the same plane, as if the galaxy itself is in the ecliptic plane, but it's anything but, as you might already know. Our ecliptic, our planets, the sun, they are tipped 60 degrees in relation to that galactic plane, to the Milky Way's equator. And that has some very interesting effects on how we see the Milky Way in the sky. This is a great example. Again, this is using stellarium. Here's the ecliptic plane where you would find the planets. And here's the galactic equator. So if you've ever gone out at night, like in the summer, and you've seen the planets down in Sagittarius, Scorpio, Libra, and then you see the Milky Way coming in at this huge angle, you might wonder, well, how does this all work? Well, it's because we're all tipped 60 degrees in relation to that galactic plane. So we have a very almost like topsy-turvy view of the galaxy. And if you add these two circles into your stargazing program, you'll see that 60-degree tilt right there in front of your face. And so this all kind of came to me one morning. I was able to visualize, you know, like you get those rare experience. I shouldn't say rare, but when you go out and you're observing and you are suddenly realizing where you're at and understanding what's around you and getting a sense of the dimension of things. This was that same place in Oklahoma. And it was on an early March morning before just before twilight started. Down here, we had the planet Venus, and here's the center direction of the galaxy right here in Sagittarius. Scorpius is off to this side. And as we move up the Milky Way, we're looking across the spiral arms through Aquila, up through Cygnus, Deneb, and so forth. This gaze continues to span the spiral arm. And for Cassiopeia, back behind us, so to speak, relative to the center. But I was standing out there that morning, and for just like 2 minutes, I had this sensation, this total out-of-body sensation that I was in space, in 3 dimensions, tipped at 60 degrees in relation to this monster galaxy. And I could perceive where I was in relation to the center and feel like I was my own observatory out looking towards the edge. It's very hard to describe, but it was a wonderful feeling. I think you know what I'm talking about because you've had the experience yourself, which is one of the reasons we love being amateur astronomers, is for those revelatory moments, right? When you're out and it suddenly occurs to you, oh my gosh, it's all making sense now. So this 3D sense of being in the galaxy materialized right in front of me. And I felt like instead of just being an inhabitant of Earth, I actually felt for 2 minutes like I was an inhabitant of the Milky Way galaxy. And it was a wonderful, big feeling, as you can imagine, because it is a very big place. And this is my final slide, but I did have a couple of other comments just about naked eye observing projects. I mentioned just 3. Obviously, there are lots of different ways that we can delve into the naked eye aspect of astronomy. Perhaps you've tried to see how many deep sky objects are visible with the naked eye. I mean, in ancient times, we only know a few of them that were handed down, like the Beehive cluster, the Andromeda galaxy, so forth. But there are at least 2 or 3 dozen that are visible if you go out and you make the effort. And that's just one idea. Another thing that is wonderful with the naked eye is to see what craters you could see with your naked eye on the moon. Now, you may not see the individual rims, but craters with rays are visible with the naked eye very plainly if you know where to look. And anything where you're using your vision and your brain, any type of connection you're making, you're going deeper into nature, you are noticing something and appreciating this. That connection is what is the source, at least for me, of so much human joy, is to be in nature, noticing and appreciating what's out there. And so that's just a couple of other ideas I wanted to toss out there as potential naked eye things. And maybe you guys have some other ideas you'd like to share with the group or with me. And at this point, I thank you very much for your time and attention, and I'm open to your questions.
Okay, do we have questions in the room here? All right, it will take me just a minute or two to walk around with a microphone because we have one microphone that we need to use for this in order to make Zoom work. And so when there's a delay here, that's what I'm doing, but we're at the first question.
I see some other questions coming up now too in the chat, I think it is, but we'll take it one at a time.
Yeah, I very much love your highlighting what you can see with the unaided eye. There are a myriad of wonderful things that are beautiful, that have all sorts of mysteries in them. And they're
Yes.
great and wonderful, and we all can do them. It doesn't take anything. I can answer 3 of your questions relating to the Earth shadow.
Great.
The reason why the Earth shadow has a very sharp edge when you're up in an airplane is because the observer is in the edge, whereas when you're on the ground, you see the edge smeared out over a large range of altitude. You have the question that why do you get that brightening when you get down low? Well, that's actually part of what happens in the ordinary dark sky. When you have a completely nighttime dark sky, you actually it brightens down at the very bottom, and they're both caused by the same effect, and that is that you have, as you suggested, you have very high extinction in that direction. The air mass goes from, what is it, five air mass at 10 degrees up or something like that to 40
Right.
air masses down on the horizon. And you just get so much scattering, so you get a lot more scattering of light. So dark skies always have that white region or lighter region along the close to the horizon. What was the third question you had?
By the way, while you're thinking of it, thank you. That's great to know about the extinction thing. That's what I was trying to get at with the scattered light looking through the extra density of atmosphere. So that's wonderful.
Right.
But the other, you're up at such an elevation. So it really, is it sort of a line of sight thing that you're actually looking through the densest part because you're at high elevation?
No, it has nothing to do with the density. What happens is when you're up in an airplane and you're in the shadow boundary, the sun is just setting for you. And so when you look along the shadow boundary, fine. When you look just a little bit above that shadow boundary, your entire line of sight is in sunlight. When you look just a little bit below that boundary, your entire line of sight is below is in shadow. Whereas when you're on the ground and you have at a similar height, your line of sight goes from dark to light, and it varies substantially with altitude. The third question you had asked was relating to that asymmetry that you saw.
Yes.
First off, you have to be careful that the Earth's shadow goes from very low altitude towards the north and low altitude to the south to maximum altitude opposite the sun. But the fact that you were talking about is definitely caused just simply by far downwind, down sun.
Down sun is good.
It's clouds far to the west of you. You can see a
Go
version.
ahead. I'm sorry, go ahead.
Anti-crepuscular rays coming in from one side. Anyway, so those are just answering your questions. But here's a question for you. I've never been able to find an answer. This is kind of the classic Don Olson question. And Don hasn't been able to answer it either. So what is the origin of the term belt of Venus? You know, it's
I have
classically
read that it has to do with a girdle or something that the goddess Venus wore. And
pink. Yeah. We've all heard that. But that's not
we've all heard that, and that's all that
came from.
Yeah.
And so you have the question, what is the origin of the term belt of Venus? And another Don Olson sort of question is, hey, who was the first person to at least have a surviving record reporting the belt of Venus? I've never been able to find that answer. And Don Olson hasn't been able to either. Anyway, I loved your talk. There are many things out there that one can go looking for. If you only have a little bit of imagination and you start looking closely, you can find beautiful things out there to look at.
It's wonderful. Thank you for helping me with understanding some of that or answering my questions about it. This is great. I figured in this group there would be somebody who would potentially have the answers to some of the questions that I had. But I don't know. It's just like, it's such basic science, I realize, but it's so much just comes through basic observation. I totally believe in new discoveries that can be made just with the naked eye, for instance. But I really appreciate your comment. Thank you so much. What was your name again? I suppose we've gone on to another person.
Just handed the microphone back. I'm Brad Schaefer.
Okay. Thank you.
Okay, do we have another question? I'm looking around trying to find a hand in the audience.
There's a question here from Terry. Should I answer it? I see it popping up on my screen.
If you would like to do that, that's fine.
Okay.
Though, Bob, read the question and then answer it. You can do the Zoom one.
I'll try to. Yes. The question is, there's mountains to the east in Tucson. Can we see Earth's shadow? You'll probably, I don't know how high the mountains are, depending on your location. If they're just near the horizon, you'll definitely see Earth's shadow come up. Maybe not the entire shadow from the very start, but it is significant. 5 minutes after sunset, 8 minutes after sunset, you're going to see that. If you see a dark gray blue band down there with that orangey top, you're definitely seeing Earth's shadow. I'd give it a try.
Okay, do we have a comment in the audience for that? No. Okay.
There were more questions too that popped up. Here we go. I'm not sure how to get to the chat though. I've got several things in chat. I see it down there.
Hang on just a second. I'll read them for you.
Okay, thank you.
Okay, from Kevin Bays, he says, I'm curious about the best method to protect the image of the sun. Can it be done without a telescope?
Oh, to project the image of the sun?
Yeah, project.
Can it be done without a telescope? I think you need a pair of binoculars. You need some optical instrument in order to project the sun into a sharp disk, obvious enough that you would be able to make out a dark naked eye size sunspot. It's weird, but maybe you've seen this in eclipses. The little apertures, the spaces between leaves in a tree, will project an image of the sun down on the ground. So you'll see the sun change phase during an eclipse, but it's soft and blurry. So you really can't use that. You need some kind of optics. You can use binoculars to do it. And then what's helpful is to take a card and place them over the eyepiece end of the binoculars to block the sunlight. And then behind the binoculars, have another piece of like white poster board and use that to project the sun on. And then you can focus it, make sure it's sharp, and then just examine your projection. So I would suggest binoculars. Cover one of the lenses, by the way. You only need one for the projection, or use the telescope Put an eyepiece in there that you don't mind getting a little heated up. In other words, a very basic, simple eyepiece. Don't put a teleview ethos in there, and make your projection that way, again, onto, say, a piece of white poster board. I hope that helps.
I have an answer to this, to that question. I used to do this with a 60 mm refractor telescope that I got for Christmas when I was 12 years old.
Yeah,
It came with Huygens eyepieces, and it produced terrific images of the sun. I used a bag or a box, a grocery box, and lined it with white paper and just tucked it under the tripod, and then took the right angle and just aimed it, that came with the scope, and
right.
with using a 20 mm Huygens, and aimed it down, and it gave some really nice images. You could see sunspots and all kinds of things, but I wouldn't recommend using it with anything bigger than that, because then you're going to get too much heat,
Yeah,
some damage. But a small scope can do it. And I did it all the time, and it's very effective.
really appreciate your comment. That's great. And it's been a long time since I've heard anybody mention Huygens eyepieces, which have pretty much been eclipsed by all of the amazing designs, current designs. But yeah, those simple eyepieces are the best because they can take the heat. They have very few optical elements, and so you don't have to worry about doing the projection.
That's right. So they're simple lenses. That's why I wouldn't recommend doing it with a Nagler.
No Naglers, no ethos, or any number of wonderful eyepieces. But yeah, that's all you need. You're absolutely right. So I appreciate that comment. Thank you for sharing it.
Okay, Bob, next one on Zoom was from Peter Jedicke. He says, thanks, Bob. Ever seen the green flash photos? That's a question.
Oh yeah, you know what? A while back, I decided to tackle the green flash because I read about how rare it was, and like all you guys, I'm a little skeptical when there's a broad claim being made. And so I thought, I'm going to go out every sunrise and see if I could spot this. And to my amazement, I was able to see the green flash and once the blue flash, like every fourth sunrise or so. So it's a little more common than I had imagined. And it is just an amazing sight. With the lake here, I get sunrises. I don't have any ability to see a sunset flash. So you just have to be there and be ready to watch it come up. And it just, for anyone who has seen the green flash, maybe some others in the group have, it really is a remarkable color. It's just vividly emerald, and it lasts, the time it lasts varies a bit. I've seen it last about 2 seconds. Maybe someone else would like to share their green flash experience. But yes, I have seen it, and I've photographed it okay on a number of occasions, but I still haven't gotten like a really good green flash image.
Okay, we do have a comment here in the room, so May's working her way over there.
All right. Thank you, May.
Oh, sure.
So last year, I was on a 5-week cruise on the western coast of Mexico. And I was seeing the green flash literally every other day at sunset. And a couple times it lasted as long as 10 seconds.
Oh my gosh, that's incredible. And were you able to get, did you take any pictures of it?
I don't know if you heard that, but the answer was no.
Oh, okay. Well, the experience is what really counts, isn't it? Obviously, I need to take some more cruises if I want to see more green flashes more easily. So that is incredible. You know, the angle of the sun plays a part too in how long the green flash lasts. If the sun is approaching the horizon at a shallow angle, as it would in, say, summertime, if it's hitting it in a shallow way, then it takes a lot longer for the sun to go down. And that potentially extends the length of the flash. When it's going straight up and down at the horizon during spring and fall, let's say, sunrise, sunset. But when it's straight up and down, the ecliptic's at a steep angle, I suspect green flashes would be of shorter duration. Again, that'd be a really great visual naked eye project to pursue, does the length of time vary depending upon the angle of the ecliptic? I suspect it does.
Okay, we'll go through a few more of these comments and questions quickly here. So from a comment from Dean Kettleson, he said, while you spoke, I reviewed images of Earth's shadow from a very clear evening at White Sands. Sure enough, the scattered band near the horizon was clearly visible. Never noticed it before.
That's great. Hi, Dean. I'm glad that you're here tonight. Yeah, it is out there, and I think that was one of my greatest pleasures was seeing that pale part of the shadow above the cows' heads. Like, wow, you get that feeling of the first time you've seen something before that's been out like literally all your life long. So that's always those kind of revelations are always inspirational.
And I think we already talked a little bit about this. Kay Lehman said, in Tucson, we have mountains off to the east. Does that obscure a view of Earth's shadow?
Yes, I think that was a similar question. And again, it depends upon your distance from those mountains. If the mountains only extend 2 or 3 degrees or so above the horizon, they're just a strip, it will not obscure your view of the Earth's shadow. You will be able to see it, not at the very beginning at sunset, but within about 5 minutes, you should be able to see it. It will be obvious. It's out every clear night. And on the opposite side of the sky, the very same thing happens when the sun rises. So the Earth's shadow then sets in the west. Everything goes in reverse. But fewer of us are up at sunrise, so I'm not as familiar with watching it then as at sunset. Maybe you have a better view to the west, is I guess what I'm saying.
All right. And then Tim Hunter just says, from the foothills north of Tucson, I see the Earth's shadow both east and west almost daily.
That, what's fascinating about it, their shadow, again, such a simple thing, but it's like, all right, it's a little exaggeration, but it's like experiencing a total eclipse of the sun every single day or something like that, we're in the shadow, the Earth is eclipsing us in a very personal way every single night.
Yeah. And then Jim Carlisle just kind of reiterated projection has to be done with refractor equipment only. Heat builds up in other types of telescopes.
Good. Yeah, that is always a good precaution for sure. If all you're interested in though is naked eye sunspot groups, sometimes you can feel free to cheat, by the way. You can look at the sun every single day and say, oh, no naked eye today. Nope, none today. Or go to the SDO site and check out the images. And if something looks like, wow, there's kind of a big deal going on here, get the filter out and take a look, see what you can see. I think it's only going to get better this year and the next as we approach maximum and solar max in July of 2025.
Absolutely. All right. And then Jim O'Connor just mentioned Susan and I use 90 millimeter with a low power colossal eyepiece to project the transit of Venus for the crowds at the biosphere.
Mm-hmm. Yeah, I probably wouldn't go more than a Plossel, for projection like that. Obviously, it works though, right? You haven't had any issues?
Yeah, it seemed to have worked. Let's see, Steve Thornton, I once saw, and a friend also saw this, a green flash from Venus when it disappeared over a low hill in Anza, California.
Oh, very nice. Very observant. That's fantastic. Who has seen, has anybody, I've seen this in binoculars, just a hint of it. Has anyone seen the green flash on the rising or setting full moon or whatever? A different phase of the moon, but full moon is usually the best. It'd be interesting to hear if someone has. But that's also something that happens that you can watch for, is the green flash on the moon. And if you don't see the green flash, one thing that you will see is dispersion. The atmosphere will spread the moon's light out spectrally so that one edge of the moon, and you'll see this at almost every moonrise if you look carefully in binoculars, one edge of the moon, I believe it's the top, will appear reddish magenta, or maybe it's reversed, and the other edge is green. And it'll stay like that for a couple of minutes till the moon gets high enough above the horizon. It's a very cool color thing. And you probably have seen it if you've ever looked at a really bright star or a bright planet near the horizon. The same dispersion effect occurs, which is, I'm always amazed at our atmosphere. I mean, we're amateur astronomers. We like looking beyond the planet. We want to get past the atmosphere all the time. But that layer of air, that onion skin layer, is like full of things, wonderful phenomena for us to enjoy, and how it affects objects that are so much more distant.
Okay, and then last question from Zoom, and then we'll see if there's any from social media. This is from Peter. It says, you mentioned crepuscular rays. Can you comment on the cause?
Yeah, crepuscular rays are caused by clouds that pass in front of the sun. And where the cloud completely blocks the sun, the cloud casts a shadow, right? But sometimes you'll get holes where beams of sunlight will go through those holes. So you get a shadow and then a pattern of beams, and you'll get a pattern of beams and shadows as sunlight works its way past breaks in clouds or gets blocked by clouds. And it creates this radiating pattern of beams and shadows around the sun. And it's really prominent when the sun is rising or setting. The rays kind of appear to go straight up, and they make this grand crown of dark and light rays above the sun. It can be an astonishing sight. Those rays, which seem to be pointed towards the sun, it's actually an optical illusion. We're looking at a vanishing point, like seeing, like standing on a railroad track and watching the rails apparently meet in the distance. Those rays, shadow, sunbeams, they're all parallel to each other, but we see them as converging on the sun. So they look spectacular. And those are crepuscular rays. And you can get them even when the sun is below the horizon. There'll be clouds there, and the sun strikes those clouds, and it casts the shadow of those clouds way up and across the sky. You may not even see the clouds, but you'll see a dappled pattern of pale light and dark beams across the twilight sky. So it can happen day or evening or early morning before sunrise.
Okay, thanks, Bob. Terry, anything from social media?
Nope, I do not see any questions here.
Okay, I need to make an announcement at this point. And all of our Facebook people particularly need to pay attention to this announcement. And that is, in the future, we're going to make a change. And instead of Facebook for our meetings, we're going to be using YouTube for our meetings. So next month, the first Friday of the month at 6:30, we'll be here. And please access YouTube rather than Facebook for us. We appreciate your coming and being with us tonight. And we hope that, again, that you look at our website, and we hope that you come back again and join us on our Friday night at 6:30. Thank you so much. Okay, and for our audience here and on Zoom, I want